All right, what's up, guys? Late video. I don't even know when this is going to be able to get up. My internet's been really poopy, so broadcasting of any kind is not happening. I mean, I'm having trouble uploading videos, like, in general, so this is taking a while. I don't know. Whatever. We'll make it work. Remember, there's no actual deadlines on this stuff. So, like, it says Friday, but you can do it, like, next week if you need to, okay? So don't worry. Don't worry. Also, I'll have a tutorial thing on Thursday at 2. Thursday at 2, I'll do a tutorial session where I'll be live. I just won't teach this. But you can ask me questions then. So Thursday at 2. And I'll post the details on the Google Classrooms. So, but let's get to this stuff. So what we're doing is we're revisiting those inverses, okay? They're going to come back up in Algebra 2 for those juniors that are moving on to Algebra 2. You seniors that are moving on with life, you know what? It's something we've done before, okay? You'll get over it. Okay, so inverses. Okay, remember, inverses, they're like flip-flops of each other. You go from one to the other. X's turn into Y's. Y's turn into X's. That's the big theme, okay? So if you've got, say, this function right here, it's a table, okay? The inverse table, remember, and then remember, inverse, it's that little like -1 thing. This means inverse, right? This is the inverse. Okay? That one will have opposite x's and y's as the original function. So remember, that's how we can tell, right? Right off the bat, here's how we can tell an x becomes a y, the y becomes the x. They flip-flop, okay? So that's something to look for, okay? We have 2 points. Again, these would be inverses of each other just because the x turns into the y turns into the x. That's what we're looking for, guys. That's the type of thing, okay? What about if it's a graph? Okay? Hopefully this is not new, okay? Again, like, hopefully this is not new. Again, if we've got a graph, okay? We've got this beautiful little graph. When we know that two things are inverses, okay? There's a line they cross over. There's a line that they're a mirror. Remember, we used to call this line right here the mirror. It's like that butterfly effect. Over here is going to be a mirror to over here. That line is y equals x. Y equals x. So we're looking at graphs. We're looking at, does it reflect over y equals x? There's another way we could tell. We could also use the points if we have two graphs, right? Maybe you're like me, you're not good with spatial stuff. So like, oh, I don't know if that's mirrored or not. Well, pick some points. Like this guy right here. This point would be what, 5, 2? Okay. We would need to have 2, 5 on the inverse. Or I think I got those mixed up. Whichever one's the inverse and whichever one's what. Okay. We would need to have 2, 5 be on this curve over here in order for these to be inverses. So I come over here, 2, 5. Oh, hey, there's that 0.25, right? X and Y flipped. Okay, that's another way we can tell. Now, just 1 point's usually not good enough. And honestly, 2 is usually not good enough either. But, because of this graph, we can only kind of see a couple. So here's another one here. 2, 1, right? So that would mean we would need 1, 2 over here. 1, 2, right? And that's 1, 2, 1, 2. Okay, so got to make sure that they're there. I don't see any other perfect points, so we're going to leave it like that. Okay, we'll just say with 2 of them. But again, there's that line, that mirror, right? If I can spell, there we go. It mirror. Okay, that mirror, y equals x. We're always looking for that one too. Okay, so let's go ahead. Let's take a look, see what this is saying. Okay, nice little example here. Really similar problem on our work this week, on our assignment, Google Classroom. Okay, so we got the following tables represent a function and its inverse. Okay, so we know these are inverses. So what do we know? We know that x better become y and y better become x. They flip-flop. Perfect. Looks like that happened again. Perfect. So that's fitting. All right. Let's recall some of those other features that inverses kind of share, but they don't really share. Like, it's kind of the same. So like here we go. It says which statements describe the functions. Check all that apply. The domain of, and again, we're looking for that -1. That means inverse, right? Okay, the domain of h inverse is the range of h of x. Well, remember, domain is the x's, okay? So domain is the x's. So it's saying that the x's of the inverse, okay, are the range of the original function, okay, this one. So that would mean that range is y's. So that means what they're saying is that the domain, so the x's, have to be the same as the range, meaning the y's. And that's true because they flip-flopped, okay? That was something we learned a while back. The domain of the one becomes the range of the other. And same thing goes for the range. The range of the original function becomes the domain of the inverse because it flips the x and y's, all right? So that's how we can do that. This one says the range of the inverse is the range of the original function. No, it's not that. We don't know that, okay? Not necessarily. And definitely not in this case. But the range is not the same as the range. They got to flip-flop. We got to remember that flip-flop. Remember when we did inverses, we were always talking about switching and flip-flopping, okay? We're not going to have things be the same. We got range and range. So those aren't flip-flopped, right? Those aren't going to be right. So that's why they didn't check mark that one, all right? They check mark this one, that first one. Domain becomes range. But range isn't the range. Those aren't going to be the same. It didn't flip-flop, okay? The x-intercept of the inverse is the x-intercept of the original function, h of x. Well, x-intercept is when y equals 0. Okay? So I see that here is the point 60. But up here, I don't see the point 60. I see 0, 6. So that would be the y-intercept, right? This would be the x-intercept here for this one because y is 0. This would be the y-intercept because x is 0. Okay? So the x-intercept of the inverse is the same as the y-intercept of the function. But again, this is talking about x-intercept both times. It's not talking about flip-flopping. It's not changing. So no, those aren't going to be the same. All right? The x-coordinate of the x-intercept of h inverse is the y-coordinate of the y-intercept of h of x. There we go. That's like a better way of saying it than I do because I say that they're the same when really they're not quite the same. It's just that that coordinate 6 is in there in both. They do share that. Okay, it's like the x-intercept becomes the y-intercept of the other. And I know that's a really simple way of putting it. I should be more like PC the way this is, but you guys know how I am. Okay, so the maximum of h of x is the largest x value of h negative 1. Now, this is something we don't usually talk about, and I actually excluded this from our thing, but it's good to talk about. The maximum of h of x. So that when you talk about maximum or minimum, you're talking about a y. So we're saying some kind of y value of the original function would be the largest x value of the inverse? Yeah, absolutely. So like, yeah, when I break it down like that, the biggest y is going to be of one function is going to be the biggest x of the other function because x's and y's flip-flop for inverses. Well, this is just a weird way of saying it, all right? So if we were in class, I probably would include something like this. But, you know, there's some nuance, some words and stuff. Remember, you can do it by hand. I don't have any questions like this, so you can pause and look at this if you want, but yeah, we're gonna just move it along here. Okay. All right, this is another little question here. Graphs for the functions and its inverse are shown on the same coordinate grid. So we got a function and its inverse, which statements accurately compare the functions and its inverse. Circle all that apply. Okay, so we're looking here. The domains of the two functions extend to positive infinity. Man, this is something we haven't seen in a while. Okay, domain is the x's. Okay, positive infinities to the right. Okay, because this is, well, domain x's. Okay, sorry, we gotta take a step back here. Domain is the x. Okay, and then extends to positive infinity. Okay, what does that mean? That means that we got an arrow going right. So do we have an arrow going right on both of these functions? Absolutely, we got an arrow going right on both. Man, this is taking way back. That's why I like this unit. Okay, so yes, we would say A, their domains do go to positive infinity. B, the ranges of the two functions are all real numbers. Ooh, man, how do we ever do that? Well, remember, to be all real numbers, you got to have an arrow left, arrow right. Well, that's for domain. Range, to be all real numbers, you need arrow down, arrow up. That covers everything. So if I look, I got an arrow up, I got an arrow down. Perfect. But then this yellow one, you're like, well, this is sort of up, but it's mostly to the right. Well, if it's sort of up, that counts as up. So this is up. Okay? If it's sort of down like that one is, like just slightly down, that's enough. It's down. Okay? So that's arrow up, arrow down. Boom. The ranges are all real numbers. Man, you didn't expect this, did you? Let's see. What else do we got here? The x-intercept of the function and the y-intercept of the inverse are reciprocals of each other. Reciprocal is a fancy way of saying flipped over. Okay? So saying that the x-intercept, this guy, okay, is going to be a reciprocal of the y-intercept of the other one. So that'd be this guy. yeah, it's like -1.5 would be like that x value there. And then the y value here is about -1.5, just about. So yeah, absolutely. Wow, ABC. It's like everything. Let's see. The point of intersection of the two functions indicates that the functions are inverses. This is a weird question. Okay, this is a weird question. It's saying the point of intersection of the two functions. So this guy right here, okay, indicates. So it's telling us, it's saying that that intersection right there means that the functions are inverses. To this, I say not necessarily. Okay, it's a hint that they're inverses. And here's why. The y and the x value are the same at that point. They're both -2. So if you have y equal x at an intersection, that's a pretty good indication. But it's not a perfect one, okay? It can happen without them being inverses. So I'm going to say not necessarily. Sure. Please don't spell check me. Okay, so not necessarily, all right? Because we do have that line y equals x. And anywhere that they actually, like, cross each other, you'd expect it to be on that line. But one point of intersection doesn't, like, it's not like a for sure they're inverses, all right? So that's why I say not necessarily. So that was a tricky one there. Okay, let's keep going. Okay, table A, Fahrenheit and temperatures and Celsius temperatures. So it's like a conversion between Fahrenheit and Celsius, all right? Table A shows the opposite. Okay, the tables show that the two functions are, this is where I'd say inverses, right? This would be inverses. Inverses. Why are they inverses? Well, check it out. -10 for x on top here becomes -10 for y down here on this one, right? 14 is y becomes x, right? Usually we go x and y and x and y, all right? Okay, my x's all become my y's. My y's all become my x's. They have to be inverses, all right? So they are inverses is what we're looking for. Flip-flopping x and y. Okay, because the ordered pair x, y for one function, so meaning like this one, is the ordered pair, well, they would flip-flop, right? If it was x, y for the one, it should be y, x for the other, right? They're flip-flopping, they're changing, okay? So that's how we can look at that. Again, flip-flopping x's and y's. All right, let's keep going. Functions inverse are shown, okay? Absolutely, that, usually I'm not too great with this spatial stuff, but that's looking pretty mirrored-ish to me. So let's look at these statements. Which statement describes the relationship between the functions and its inverses? The range of both is all real numbers. The range of both is all real numbers. Well, this just so happens to be an expo function, okay? Hopefully y'all can recognize that. We did a little bit of that last week, all right? The inverse of the inverse of an exponential, I just gave it away, is a log function, okay? It's a log function. So we know from exponentials that there's this asymptote, okay? It's that line it can't cross, okay? If we're saying the range is all real numbers, well, that would mean we need an arrow down from this yellow guy, and I don't see it. It doesn't happen, right? It stops at that barrier, that asymptote that expos have. So no, can't be E there. No. The domain of both is all real numbers. I have the same argument now for the log function, all right? We need an arrow left, arrow right for domain to be all real numbers, and this one does. We got an arrow right here, but I argue there is no arrow left because that asymptote for the inverse flips. Now it's a vertical asymptote. So this guy can't cross. It can't cross this guy right here. So no. Okay. The range of f of x is y greater than 0, and the domain of f inverse is x greater than 0. So remember, range is y, so it's saying y greater than 0. So 0 and everything bigger. So arrow up. Absolutely. That's a true statement. And then the domain of the inverse, x greater than 0. Well, it's definitely going to be big because it's getting bigger. But does it stop at 0? Well, there's that asymptote. That's x equals 0. So yeah, it's from 0 and then anything bigger than that. So yes, this would be true. The domain of f of x is x greater than 0. And the range of f inverse is y greater than 0. Well, I can debunk that right now. Y greater than 0, I cross that right here. Look, there's negative y's right here for the inverse. So no, that can't be right. Boom, you just need one example to make something not right. So yeah, that doesn't work. Also, it says x has to be greater than 0. We got negative x values right here. So no, No, that's not true. So the only one on there was just G. All right. Some domain and range. Whew. All right. All right. Here we go. Here we go. Here we go. Oh my gosh, there's so many words. Do I need this? I don't think I do. Well, nah, forget it. All right. It's a scary word problem, but forget it. All right. So we got a function that models the stopping distance of a car. Okay, table B models the velocity based on the feet it took the car to stop. Okay. When verifying the relationship between the functions using their values in the tables, what conclusion can be made? Since the functions in both tables are increasing, they are inverses. That has nothing to do with inverses. We don't care if they're increasing, decreasing, or whatever. We say we're looking for flip-flopping, we're looking for mirrors, we're looking for x's switching with y's. No, that has nothing to do with that, okay? Increasing. That describes functions and like stuff like that. Like we do that in a different part. No, we're not dealing with that right now. Let's see. Since the functions in both tables are increasing, they are not inverses. Again, increasing, decreasing doesn't affect whether or not things are inverses. All right? That's not what we look for. Let's see. C. Since for each ordered pair x, y, for one function, there's an ordered pair y, x for the other function, the functions are inverses. So what that's saying is you got x, y, and then those values flip-flop to y, x on the other one. Then those should be inverses. That's what I see going on, right? X turns into y, y turns into x, and then that happens for all three of those points they've got. Bingo! C was it. Let's see what D says, just to see. Let's see. So since for each ordered pair x, y for one function, there is an ordered pair y, x. Okay, that's the same. For the other functions, the functions are not inverses. Okay, that was the difference they put in there. They're not. Nope. It's C. We want to see that flip-flopping. We want to see that x switching with y and vice versa. That tells us that those are inverses. Okay. Lastly, let's just do this last one here. Okay. Let's see. The cost table shows the average cost of producing X number of earbuds. So we just got a function. We don't have an inverse. Let's see. When verifying that a function represented in another table is an inverse of the given cost function, which ordered pair can be expected? So if we knew we had an inverse, if we knew that we had that a to the negative 1x, right? It's saying what points would we expect to see in here? That's what it's saying, right? X's are going to switch with Y's. X's are going to switch with Y's. X's are going to switch with Y's. Okay? That's what we would expect from the inverse, right? So let's look. Which one of these points are over here? Let's take a look. So I see, wow, they're doing the 52 and the 20 thing for sure. They're not going to be the same because we're just flip-flopping X and Y. So it would be X would need to be 52. Yeah, that one right there. Okay. And then Y would be 20. We're flip-flopping. Okay. So what would you expect to see in an inverse table? You would hope to see that point right there, or else there aren't going to be inverses. All right. So that's inverses. Again, this is kind of like a review. I kind of like that they went this route. It's kind of nice that we're kind of like reviewing things. I think that's a good culmination of everything that we need for Algebra 2 for y'all moving on, and especially y'all moving on to college. Good base stuff for y'all there. Tuesday. Hopefully I can get this fixed by Tuesday, and I'll be on my tutorial session then. I'll have the details on there. I have no idea when I'm going to get this uploaded to the YouTube channel. Just remember, don't panic. We have deadlines, but they're deadlines, okay? Just get all your stuff done before the end of school. All right? Any questions, email me, whatever you need, all right? Happy studying.